Ever hit that undo button and just felt like a weight lifted off your shoulders?
Oh, yeah. Like deleting a whole paragraph you messed up. Ugh, technology.
Like you could just magically rewind. It's so useful. And, in math, there's a similar kind of magic, like an undo button for a specific operation.
Yeah.
And today, we're diving deep into that integral calculus. It's like the reverse of differentiation.
Exactly. Differentiation, if you remember, it's all about finding how fast something's changing.
Yeah.
You got your curve. Differentiation gives you the slope at any point on that curve.
Mm-hmm.
But integration kind of flips the script.
It does.
It asks, well, if we know the rate of change, can we figure out the original curve? Kind of like having footprints and trying to retrace the steps, you know?
That is a perfect analogy. And in this deep dive, we're going to explore exactly that. We've got some really interesting stuff from a math textbook chapter to guide us. Now, calculus, it might sound a bit, specialized.
Yeah.
But honestly, the principles behind it, both differentiation and integration, they're surprisingly fundamental.
Oh, absolutely.
It's like all over the place. Our source talks about science, engineering, but also economics, finance, even probability. It's amazing how often change and accumulation come up.
It really is. From like disease spread to stock market swings to, well, you name it. Calculus gives you the tools, the language to understand these things. And sure, it can seem complicated at first, but the core ideas are pretty elegant. They build on each other, you know?
They do. So our mission, if you will, is to grasp those core ideas of integration,
Right.
to see how it undoes differentiation, get comfy with the basic formulas and all that, and ultimately really get what it's all about. We'll break it down step by step, so don't worry. No one's getting left behind. Okay, let's unpack this whole integration as the inverse of differentiation thing. What's that actually mean in practice?
Okay, so basically we're trying to find a function when all we know is its derivative. So let's say we have a function, call it f of x, and we differentiate it and we get f of x, right? Well, then we say f of x is an antiderivative of f of x, sometimes also called a primitive, and finding this antiderivative, this original function, that's integration.
I see. And our source has some great examples to make this crystal clear. Like, remember, the derivative of sine x is cosine x. Well, it means sine x is an antiderivative of cosine x. Simple as that.
Right.
Another one, the derivative of x cubed divided by 3 is x squared. So x cubed over 3 is an antiderivative of x squared. And here's a fun one. The derivative of e to the x is, well, itself e to the x. So it's its own antiderivative.
Exactly. You see that inverse relationship perfectly. But there's a catch. These antiderivatives, they're not unique.
Oh.
Yeah, think about it. The derivative of any constant number, doesn't matter what it is, it's always 0, right?
Yeah.
So if sine x is an antiderivative of cosine x, then sine x plus 1, sine x minus 5, sine x plus a million, they'll all have the same derivative.
Yes, the arbitrary constant, the good old plus c. So when we find an indefinite integral, we got to add that plus c at the end to show there's a whole bunch of functions that could have the same derivative.
Precisely.
It's like finding the basic shape, but you can shift it up or down however you want.
Exactly. It's a whole family of antiderivatives. And this leads us to how we write an indefinite integral. Our source lays it out. The indefinite integral of f of x with respect to x is written as, well, you got that integral symbol, f of x dx equals f of x plus c.
Okay.
So f of x is the integrand, what you're integrating, x is your variable, and c, well, that's our constant of integration. And the integral symbol itself, it almost hints at summation, which we'll get to later with definite integrals.
It's like we're given the end result of a rate of change problem, the derivative, and we're going back in time to figure out the original function.
Yeah.
And that plus c is there to remind us, hey, there might have been a constant term in the original function that vanished when we took the derivative.
Right. And there's this interesting point in the source about functions with the same derivative over an interval. It basically says if you've got two functions, g and h, and they have the exact same derivative across a certain range, then the difference between them has to be a constant. So if the rate of change of that difference is 0 everywhere, it can't be going up or down. It's got to stay constant.
It's like if your speedometer is stuck at 0, your mileage isn't changing, you're not moving. Makes sense. Okay, so we've got integration as the opposite of differentiation. We understand antiderivatives, and we know about that all-important c. Now, just like there are formulas for derivatives, are there shortcuts for integrals? Because constantly guessing the original function seems, well, inefficient.
You bet there are. Our source points out that for every standard derivative formula, there's a corresponding integral formula. It's just a matter of knowing your differentiation rules.
Right. If you know what happens when you differentiate, you automatically know what happens when you integrate the results.
Exactly.
And our source has a handy list of these standard integral formulas. Like one of the most basic ones is the power rule for integration. The integral of x to the power of n is x to the power of n plus 1, all divided by n plus 1 plus our constant c. Works for any n except n equal 1. And when n is 0, meaning we're integrating just 1, the integral is simply x plus c.
That power rule, it's like the bread and butter of integration.
It is. And then we got the integrals of those basic trig functions.
Yeah.
So since the derivative of sine x is cosine x, the integral of cosine x is sine x plus c.
Right.
Got to watch those signs. The derivative of cosine x is negative sine x. So the integral of sine x is negative cosine x plus c.
It's that negative sign that always gets people.
It does. It's easy to forget when you're working backwards. And the list goes on. The integral of secant squared x is tangent x plus c. The integral of cosecant squared x is negative cosecant x plus c. Secant x tangent x integrates to secant x plus c. Cotangent x integrates to negative cosine x plus c. It's like a dictionary of reverse differentiation, really.
It is. And don't forget the integrals related to inverse trig functions, like the integral of 1 over the square root of 1 minus x squared. That gives us arcsine x plus c. And the integral of matif 1 over the same square root, that's arcosine x plus c. Super useful when you're dealing with expressions that might have come from differentiating those inverse trig functions.
So it's good to remember, these integral formulas aren't just random rules. They come directly from the derivative rules we already know. Having these in our toolbox is going to be super handy for tackling tougher integration problems.
Yeah.
Just like knowing our basic derivatives helps us with complex derivatives.
Exactly.
But what happens when we encounter a function that's, well, not so standard, like it's a mix of different functions, or a constant times a function?
Then it's time to use the properties of indefinite integrals. They help us break things down into more manageable pieces. One of the most basic ones is that whole inverse relationship we've been talking about.
Right.
You integrate a function, then differentiate the result, boom, you're back to your original function. And the other way around, you differentiate, then integrate, you get the original function back, plus our friend c, of course.
So it's like saying, if you freeze water, then melt it, you get water again. And if you melt water, then freeze it, you still get water, but maybe a little bit evaporated. That's our plus c.
That's a great way to think about it. And then there are the linearity properties. They basically say the integral of a sum is the sum of the integrals.
Okay.
So if you've got the integral of f of x plus g of x, you can split it up into the integral of f of x plus the integral of g of x. And if you've got a constant times a function, you can pull that constant out. So k times the integral of f of x is the same as the integral of k times f of x, where k is just any number. This makes things like polynomials way easier to handle.
Right. You can break them down into smaller, more familiar integrals that you might have a formula for.
Exactly. And the source points out that these linearity properties work for any number of functions you want to add or subtract.
Yeah.
So you've got a whole string of terms. Just deal with each one on its own.
That's super convenient. So we've got the basics. Integration's the reverse of differentiation. We've got our list of handy integral formulas, and we know about these linearity properties to simplify things. But what if we stumble upon a function that doesn't match any of our standard formulas, even after using linearity? How do we actually find the antiderivative then?
Well, that's where the fun begins, with the different methods of integration. Our source gives us a peek at some of the key techniques. Sometimes we can just find it by inspection, by just looking at the integrand and thinking, what function's derivative would give me this? Like recognizing a familiar face in a crowd.
Right. The source gives the example of cosine of 2x. We know the derivative of sine of 2x involves cosine of 2x because of the chain rule, right? So we could figure out that 1/2 sine of 2x would be an antiderivative.
Exactly.
It's like solving a riddle by looking for clues.
Right. Another example is 3x squared plus 4x cubed. We know 3x squared is the derivative of x cubed, and 4x cubed is the derivative of x to the fourth. So the antiderivative of the whole thing is just x cubed plus x to the fourth. And for 1 over x, well, its derivative is ln of the absolute value of x, so that's its antiderivative.
Okay, but the source makes it clear that inspection only takes us so far. Not every function is going to be that obvious. So what do we do then?
For those tougher cases, we need more powerful tools. One of the most common is integration by substitution.
Mm,
It's all about changing the variable to simplify the integral into something we can solve with our formulas, like translating a sentence into a language you understand.
okay.
You pick a part of the integrand as your new variable, and hopefully the rest of the integral transforms nicely too.
And our source gives examples of when this might be useful, like integrating sine of mx by substituting for mx, because its derivative is just m, a constant. Or integrating 2x sine of x squared plus 1, where if you let u equal x squared plus 1, its derivative is 2x, which is already there in the integral.
Hmm.
So you're looking for a function and its derivative lurking in the integrand.
Exactly. If you spot that, substitution is probably a good bet.
Okay.
The source also mentions using substitution for trig functions, which leads to those standard integrals for tangent, cotangent, secant, and cosecant.
Makes sense. And then there's integration using trigonometric identities for integrands with trig functions.
Right.
We've got a whole bunch of trig identities that can transform expressions into something easier to integrate, like integrating cosine squared x by using the double angle formula to rewrite it in terms of cosine 2x, which we know how to integrate.
Exactly. These methods, inspection, substitution, using identities, they're the foundation of integration techniques. And as you go deeper, you'll find even more advanced methods for more complex integrals.
Okay, now about that constant of integration, c, it represents a whole family of antiderivatives, right?
Right.
But in real-world problems, we often need a specific antiderivative that meets a specific condition. How do we find the exact value of c?
The source shows this with an example. Let's say you've found the indefinite integral and you have a general antiderivative f of x plus c. And you're given extra information like the value of the antiderivative at a specific point, say f of 0 equals 3.
Right.
You can use that to solve for c.
So if we had f of x equals x to the fourth minus 6x plus c, and we know f of 0 equals 3, we just plug in x equals 0 and set the whole thing equal to 3. That gives us 3 equals c. So the specific antiderivative is f of x equals x to the fourth minus 6x plus 3. It's like we're picking one specific curve from that whole family by giving it a fixed point.
Precisely. That extra condition tells us one point the graph has to pass through, and that locks down the constant of integration.
It's fascinating to see the similarities and differences between differentiation and integration. Our source has a whole section comparing them. What are some of the key takeaways?
Well, both are operations on functions. You put a function in, you get something else out. For differentiation, it's another function, the derivative. For integration, it's a family of functions, the antiderivatives.
Right. And both have that linearity property we talked about. You can differentiate or integrate a sum term by term and factor out constants.
But there are differences too. Not all functions are differentiable everywhere. You can have points where the derivative just doesn't exist, like a sharp corner on a graph. And not all functions have a simple, neat formula for their indefinite integral. Sometimes the best we can do is represent the integral as another function defined by the integral itself.
It's interesting that even in math, there are things we can't express easily.
Absolutely. And another key difference is uniqueness. The derivative, if it exists, is unique, but the indefinite integral is only unique up to that constant c.
Right, right.
Any two antiderivatives of the same function, they'll differ by, at most, a constant.
There's also that opposite effect on polynomials. Differentiating a polynomial, the degree goes down by 1. Integrating a polynomial, the degree goes up by 1 usually. They kind of work in reverse.
Yeah, that's a good point. And we can talk about the derivative at a specific point, but the indefinite integral is defined over an interval.
Right, right.
Later in the chapter, we'll see how definite integrals are all about integration over a specific interval, with start and end points.
Ah, so the indefinite integral gives us the whole family,
Mm-hmm.
and the definite integral gives us a specific value for a specific range. Yeah. The source also mentions the geometric interpretation. The derivative is the slope of the tangent line at a point.
Right.
What about the indefinite integral geometrically?
It represents a family of curves, all with the same derivative. They're just vertical translations of each other, same shape, shifted up or down. That's our plus c in action. When we find a specific antiderivative by finding c, we're picking one particular curve from that whole family.
And finally, the source reminds us that both differentiation and integration are tied to limits. Differentiation is defined with a limit, and definite integration also involves limits, as the limit of a sum, apparently.
Exactly. Both are cornerstones of calculus, built on that foundation of limits. And of course, the big one, differentiation and integration, are inverse processes, the mathematical undo and redo, just like we've been talking about.
It all comes together so nicely. We've covered a lot of ground here, From the idea of reversing differentiation to understanding those standard formulas, key properties, and even a sneak peek at some methods for finding integrals.
We have. We've seen how integration lets us undo finding rates of change and how it gives us whole families of functions with the same rate of change. And we've got a starting toolkit of formulas and properties to help us explore further.
So, listener, as you think about this deep dive into indefinite integrals, consider this. We've seen how finding a rate of change can be undone by integration. Can you think of other real-world processes that have a natural reverse operation, like maybe energy changing forms, or a system evolving and then returning to a previous state? Thinking about these reversals might give you a new perspective on things.
That's a great point to ponder. And if this has sparked your curiosity about definite integrals and more advanced techniques, I definitely encourage you to check out the rest of the chapter. There's a whole world of calculus waiting to be discovered.
Absolutely. Thanks for taking this deep dive with us. Until next time, keep those minds curious.